Support for today's Heat Treat Radio episode is provided by Heat Treat Bootcamp. Find out how you can enroll in this basic training at www.heattreattoday.com/bootcamp. And welcome to Heat Treat Radio. Whether you're listening to us or tuning in via video on heattreattoday.com/radio, we're glad to have you. Scott MacKenzie, the Senior Research Scientist and Metallurgist for Quaker Houghton, is joining Heat Treat Radio host and Heat Treat Today publisher Doug Glenn to talk about 4 need-to-know topics for heat treaters in the automotive industry. Scott speaks from his expertise in quenching to share his thoughts on major topics ranging from electric vehicles, aluminum and automotive manufacturing, simulation and design, and where to get heat treat and quench training. Let's take a listen.
Hi, everyone. Welcome to another episode of Heat Treat Radio. We're here today with Dr. D. Scott MacKenzie from Quaker Houghton. We're going to talk a little bit about quenching. Scott, first off, welcome to Heat Treat Radio.
Thank you.
Going to do a quick introduction.
And I just go by Scott.
You go by Scott. All right, very good, very good. We could. You and I have known each other long enough. I can probably do that and get away with it. So that's okay. But anyhow,
everybody calls me Scott. I don't like being called doctor. So
okay, all right, there you go. Well, let me give the folks a bit of an intro, and then I'm going to just kind of highlight some of the stuff we're going to be covering today, which includes things like we're going to be talking quenching, because Scott obviously is the quench king here, and we're going to talk about EV, electric vehicles a little bit. We're going to talk about aluminum in the automotive industry, modeling and simulation. We're going to talk about briefly, we're going to talk about a product that Quaker Houghton came out with not too terribly long ago called Greenlight. We'll talk about that just briefly. We're going to talk about training for captive and or commercial heat treaters in regards to quenching. So that's stuff to look forward to. But first, let me just mention that Scott is presently the Senior Research Scientist and Metallurgist for Quaker Houghton, formerly Houghton International in Quenching, PA. He joined Houghton International in 2001 as a technical specialist, heat treating marketing, and moved to the heat treat laboratory to the supervisor position in 2007. Prior to joining Houghton, he worked as an associate technical fellow and failure analysis at the company actually for 6 years, and manufacturing engineer for the steel and aluminum heat treating departments for 12 years. He was past president of the IFHTSE, International Federation for Heat Treatment and Surface Engineering, from 2018 to 2020, and is an active member of ASM, served on a lot of committees over there at ASM, I know, as well as member or chairman. And you've authored, Scott says here that you've authored several books and over 100 peer-reviewed papers. So Scott got his BS in metallurgical engineering from the Ohio State University. Go Buckeyes. Copyrighted. There you go. Absolutely. You got to say the Ohio State.
The copyright that has a trademark on it.
And got your, looks like your MS and PhD from the University of Missouri, Rolla. So that is, bottom line, Scott is well qualified to talk about quenching, and that's what we want to do. Scott, before we jump in and ask the first question, anything else you'd like to share with us about your background, where you've been, some of your more interesting experiences, or, things that would be of interest?
I got my PhD late in life. I started on my PhD when I was 45.
Right.
So I already had, practically 15 years of experience on the shop floor, mostly doing heat treat with doing all the landing gear for the F-18, F-15, AV-8B Harrier, wing skins for aircraft like the MD-80, DC-9, DC-10, MD-11, and then some of the, then later when it was Boeing, it was some of the 737 wing skins and all that sort of stuff. So
yeah,
there's just a lot of manufacturing on the shop floor.
Right. And it's a real it's a real
It's
advantage
good.
going to school late in life too, I think, because you come there with a real different perspective. You're not green, you know the questions to ask, you know what's BS, what's not BS. So
Well, the trouble is with that is twofold. One, you're not willing to take any BS from the professors, right?
right, right.
Right. And also you are more willing to challenge them.
Yeah.
Okay.
Right.
So in that, you're from a teacher's perspective, you're a much more difficult student.
Yeah.
Okay, because they question more. But by the same token, you're also easier to teach.
Yeah.
Because they're more motivated. You're not just there because mommy's paying the bill.
Yeah, absolutely. Absolutely. I'd much rather, I mean, I taught school a little bit, not college level, but much rather have students that are engaged. So that's good. All right. Well, listen, let's you, I, and the four horses of the apocalypse. Let's start making, which I love the background, by the way. Let's talk about electric vehicles. All right. It's a transition that seems to be coming on. Let's talk about it in terms of heat treating in general and quenching in particular, if you don't mind. What do you think about this EV thing? How's it going to impact heat treat?
Well, there's a big thing about EV that's going to drastically impact heat treating in the heat treating industry, as well as quenchings. Presently, approximately 50% of the heat treaters, at least in the US and probably globally, are related to heat treating of gears, right? Transmission gears, etc. Right? Then we have, doing other suspension components, like the tulips for the drive shafts, etc. Right? But should the complete EV be, and I'm not talking hybrids, I'm talking about a complete EV. EVs drive by, you push your foot on the accelerator, it goes through like a potentiometer, the computer, and that will control the four motors at each wheel, or just two, all right? There's no transmission involved. So since there's no transmission involved, there's no requirement for gears. And since there's no requirement for the gears, there's no requirement for heat treat. And so if we get a full implementation of electric vehicles, we'll have roughly 50% excess capacity in the heat treat industry, which means the grid people won't be selling as many grids. The quenching people won't be selling as much quenching. You will still have, even in the racing world, like even Formula One is going to electric. They have Formula E, which is all electric. You look at even the supercars. Aston Martin just announced a fully electric vehicle. Okay, I mean, came out with their Twitter feed last night. I'm a big fan of Aston Martin. You have the Lamborghini, Ferrari. They're all coming out with electric vehicles, either hybrid or fully electric. Volvo is committed to 100% electric by 2025.
Right. I've seen that. Yep.
So we need to pay attention to where the industry is going. Now, you will still need the suspension components, for instance,
Right.
the tulips, that, the drive shaft, where the motor attaches to the wheel and that shafting, but that will be predominantly not by traditional atmospheric quench. That's going to be done by induction hardening.
Okay. Yep.
And so I expect to see an increase in induction hardening, or at least stay the same, but more traditional atmosphere, endothermic atmosphere, and quenching, that's going to be drastically hit in the next
Right.
5-10 years.
Right. So gears, I assume camshafts, not going to
Yep.
see that.
Yep. Other than
drive shafts to a certain extent, not the same type of drive shafts that you've got now, right? But those different types. There'll be 4 independent ones, I suppose. Does the EV move add anything? Are we doing heat treating of armatures or anything in the motors, motor laminations, anything of that sort? Does it add to the heat treat load?
I mean, certainly the motor laminations, that requires a special process, a thermal process. It's not
Yeah.
quite heat treating because the thermal lamination, it's going to require different materials, higher silicon steels. You are also going to see much more, leading into your other question about aluminum heat treating, because of the structures are going to be moving in either much higher strength steels for bodies to meet crash worthiness. They're either going into aluminum because of lighter weight, or for very high performance, they're going to go into carbon fiber. Okay, I mean, that required, carbon fiber will require, the resins and the prepeg and all the, will require thermal process in itself. But that's more like in an autoclave, right? Not like airframers do. Aluminum will require a different mindset, all right? This will require, and it's already starting to happen, where automotive manufacturers are starting to do aluminum heat treating. And a lot of them are adopting a lot of the aerospace specifications, for good or bad, like AMS 2770, for heat treating recipes. It eliminates a lot of research and development on their part.
Right. So they just have to stick to the AMS 2770.
Or you can do like the Japanese have done in many cases, where they're not going to aluminum. What they're doing is higher strength steel and just making it thinner. And they're going through and using special designed steels, much more highly refined grain. You've got other stuff in there, you've got some rare earths and other stuff to get the high hardness. And then what they're doing is, for instance, they're forging it at a high temperature, and the Germans are also doing this too, as part of Audi and Mercedes, is they forge the sheet, they take the cold sheet, they put it into a forging press, they heat it up to the forging temperature. Then what they do is that then they stamp it into the sheet, into the form, very complicated form, right? And then what they do is that they quench it while it's in the plat. So in other words, they have all kinds of holes in the die, and so it's actually acting like a quench press, but in this case, by a quench press. So then they have a fully heat treated part as it exits forging press.
And that was steel or aluminum?
Steel.
That's steel. Okay. High strength steel, specially designed, let's say designer steels or whatever. Okay.
And so all it does is that it goes, once it gets out of the forge press, it's stamped.
Yep.
And then goes out. It goes directly into the tempering furnace.
Okay. Yep.
And this is done, and sometimes it goes directly out without tempering. It gets painted and then puts into a curing, and that does my tempering operation.
Does a tempering. Okay. So does that, as far as the quenching part, obviously you're quenching through the die, as you mentioned. So that's changing. Is any impact? Is it the same type of polymer quenching, I assume?
No, it's just the mass of the die.
Okay.
They may use air and the mass of the die, just the large, when you think of it.
Yeah.
A die has to be very large.
Yeah.
Compared to my sheet metal, in
Yeah.
terms of thermal mass. So they're using the thermal mass of the die to quench the part.
Which they're obviously cooling that die because it's going to be warming up as you. Okay. Gotcha. All right. Very interesting. So just
one of the problems is cooling the die.
Yeah.
Cooling the die quick enough. So they have to use all kinds of very special channels and high velocities of water, etc.
Right. Very interesting. So just a quick editorial comment about this. So there's a debate out there. Maybe you can comment on this if you'd like, Scott. Debate out there in the green world regarding the use of aluminum panels versus steel in the automotive industry, with body in white type of panels for cars. those who are green seem to be, they say, well, we need to push for aluminum. But the fact of the matter is, aluminum takes a lot more energy. It actually has a higher carbon footprint to produce than most steels do when the steels are created. So it's an interesting thing that the Japanese and the Germans are moving towards custom designed high strength steels as opposed to potentially aluminum. What do you think?
Well, I mean, if you look at aluminum, and it depends on at what point in the process you look at. If you look at just the overall of aluminum, all right, because of the high degree of recycling of aluminum, okay, we're not mining anything. We're not mining bauxite, okay? So all of it goes in, and then it's already. So all you have to do is melt it and alloy it, or grade the alloy. So instead of making it with the high energy cost of the bauxite process, all right, which is interesting, it's some of the cheapest. It's up in Iceland. I mean, just tremendous because of the cost of electricity. And it's really interesting seeing those in Iceland. Anyway, that's neither here nor there. So if you look at the whole process, you know, from a cradle to grave aspect, aluminum is very attractive. Steel, on the other hand, while we're doing a lot more recycling, and we're putting it in instead of the old process where you take the taconite and you make a series of blast furnaces, and then you put it into a mixer, and then you put it into the open heart or BOF, and cast and ingot, etc. Now we're running scrap, nearly 100% scrap, in an electric arc furnace, put in a continuous caster, and out. All right. So from just electricity required to melt it, it's obviously doesn't take as much electricity to melt aluminum as it does steel, just because the temperatures are different. Okay, looking 2,700 versus 1,200 for aluminum. So in terms of an environmental impact, you know, you have to look at all the numbers. But I suspect that aluminum would come out the winner.
Okay, interesting.
Because you're not have to mine it.
Yeah, interesting. All right, let's talk about this. Our next topic I want to talk about with you is simulation and modeling, because we've talked a bit about that offline, and just the developments there. As far as quenching goes, what can you tell us in the quenching world as far as simulation and modeling? What's happening?
Well, it can be done, and it can be done accurately.
Yeah.
Okay? But all right, part of that is dependent upon the quality of your materials data. Okay.
Okay.
That's the part. Okay. We need to know how that will respond as a function of, you know, the constitutive equations within the part. For instance, you know, if I put a stress on it, or I put a strain on it, what's the plasticity of the part? How will it deform?
Yeah.
All right. The next thing you have to understand is the quenching itself. You have to understand the physical properties. When we look at the heat transfer, so we have to look at the temperature, we have to look at the thermal conductivity, thermal diffusivity, as well as the position in space, X, Y, Z, as well as time, because, you know, obviously it's a time function, all right? So we have to understand that within the part. Now we also have to do the same sort of thing on the quenching, but now it's a function of space on the surface of the part. All right, so now we have to look at velocity. We have to look at surface temperature, velocity, thermal conductivity, as well as X, Y, Z, and time, all right? So those things that's why there's been so much modeling and good effect with, for instance, high pressure gas quenching because the properties of the gases used are well known, well documented. You know, you just look them up in a table someplace. The quenchants, on the other hand, the quenchant suppliers have done a lousy job of documenting the properties, the thermal properties. That's starting to change. Right? So that's one of the problems that we see, is that the thermal properties of the quenchant are not well established. The second thing is looking at the boundary conditions of the part. Right? Is that changes as a function of position and agitation. Right? You know, the agitation rates can change, you know, around a part. You know, if I look at a part, let me do the nice video. All right. The quench rates change as a function of velocity. Well, the suppliers have not done a real good job of characterizing their quenchants as a function of velocity. All right, and so that's a problem, right? That's getting worked on, right? So in terms of the simulation, it can be done if you've got good boundary conditions. The boundary conditions being the stuff on the outside of the part and the stuff inside the part. Once you do that, and you can do this with either using, you know, something like computational fluid dynamics, okay, and then applying that as whatever velocity heat transfer coefficient that you get out of that, and apply it to the boundary of the part, then you can use, you know, a variety of different software programs such as Dante, or Transcolor, SimHeat. Both of those are good. Just the difference in their material databases. Each will give similar results, but it's a function of garbage in, garbage out. You know, you have to have good material properties and good boundary conditions. If you have those, then you can get a reasonable result. But if you don't, you'll just get garbage results.
Yeah, yeah. Do you see, Scott, there's, I guess as far as simulation goes, obviously it's something that can be done. Do you see it growing, the use of it growing significantly over the next 5 to 10 years? And if so, any particular areas do you see it growing? I'm assuming it's going to be in high value parts, right? You're probably going to probably see it more there than in your, you know, nuts and bolts.
I see it more in, you know, agreed, like in the higher value parts.
Yeah.
And also induction hardening.
Okay.
All right. And let me explain. One, in the high value parts, because they want to be able to characterize the parts. All right.
Yeah.
Either as, oops, I sent this part out and it cracked. What happened? As an
Right.
analysis tool to prevent, either to explain things why something broke. I see this occurring more in the automotive world at the OEM level.
Okay.
You see some of it in the second tier aerospace, you know, where they're trying to understand to reduce residual stresses, reduce distortion.
Mm-hmm.
At the commercial heat treated, no.
Yeah. Yeah.
They just get paid to quench the part and shove it out the door.
Yeah. Okay. And is it genuinely accessible today? I mean, you mentioned Dante and things of that sort. I mean, are most of the quench companies doing, I know Quaker Houghton probably is, but are most of the quench companies working with modeling, or is it not that commonplace?
It's not that common.
Okay. All right.
Part of it is because, you know, the quenchant business is a very competitive business. Right? I mean, it just is, and a lot of people look at it as strictly a commodity. And I mean, quite frankly, we've lost sales, I've lost sales over a penny a gallon. All right, and so one of the things is it's very difficult, and it's more difficult for the salespeople. You know, I'm not in sales, but lab guy. But is to look at the value add. Right, and that value add can either be, you know, we're not the cheapest quenching out there. Okay, we're not. That's, you know, we're the Cadillac, we're not the Chevy. All right. So to justify that higher price in my salary, you have to, you know, we have to sell the value add, and that value add can be help with making sure that the quenchant meets, or rather that when I quench my parts in it, I'm going to make properties. Okay. For instance, most quenchant suppliers do not have a metallurgist. Okay. One, metallurgists are hard to find anyway. Okay. So they'll get a material science person, which may or may not be exposed to heat treating. So they have to help them understand whether or not they're going to make parts. In other words, to mitigate the risk in changing to another quenchant. Right. So the value add is, you know, the backup support from a metallurgical point of view. You know, that's help understanding not only just the chemistry of the quenchant and what it does, but what happens to the part. You know, why has my part stayed? Or why did my part crack? Or why did my part work this way as opposed to that way? How can I improve the residual stress state in that part? How can I reduce the distortion? How can I achieve better properties? Those are the things that, for instance, we can help with. All right. But some of the other suppliers can also do it, but they're not doing it using modeling or using, you know, computational fluid dynamics or using, you know, the modeling program. They're doing it based on their experience. Well, something I do too, but I can do that with the modeling and my experience.
Yeah.
Even closer.
Yeah. Yeah. Two prongs there.
Did that answer your question?
Yes. Yeah. Yeah. Basically, I was trying to get a sense from our listeners, who are many of them are going to be, you know, manufacturers with heat treat in-house, captive heat treaters, as we call them. Just curious how accessible it is. You know, do they need to? Is it something they can call today and say, you know, can you help me with this? And can we model it? Sounds like yes, but not with all quench suppliers. But it is possible. I guess there
are also consultants out there.
Correct.
We'll be back in just a moment. But first, take a minute to sign up to go to Pittsburgh this October 2022. This fall, Heat Treat Today is hosting the first ever Heat Treat Boot Camp, a basic training to benefit new hires and old hires who want to learn about how the North American heat treat industry works. We're talking the main players, products, processes, markets, and materials in the North American heat treat market. That is, who are the main equipment and service suppliers? What products are they selling? What are the popular processes in heat treat? What markets is heat treat most important to? And what materials are most often heat treated? This is the perfect training to help you walk and talk the industry and will not be overly technical. Go to www.heattreattoday.com/bootcamp to register for the 3-day training in Pittsburgh. Again, that's www.heattreattoday.com/bootcamp. Now, back to the episode.
Let's talk about quickly. The Quaker Houghton came out, I don't know, several years ago. It's probably been over 3 or 4 years ago.
3 years.
What's it?
3 years.
How many?
Next month.
3 years. Okay. Came out with this product called Greenlight, and I've been wanting to talk to somebody over there about that. So just 30,000-foot view. What is it? Why does it work? Why should people care about it?
Okay. What the Greenlight unit is, and it's very simple. You're measuring something.
Yeah.
All right. And that measuring something could be, for instance, polymer concentration using a micrometer. There, you could be measuring pH. You could be measuring some other physical property. right? You tell the unit, these are the ranges that I want to use. You can use it through a computer interface or PLC interface. And I set this box on, for instance, my induction hardener, which is very common. I have a concentration range for the polymer quenchant.
Yep.
All right. If I go below that, it puts a big red flag.
Got it.
Right. If everything's good, it waves a green flag. If it's either too high or too low, it waves a red flag and says, pay attention. All right. Now, that red flag can be either I could add water or add polymer, and I could tell either a person to do that, operator, come and do this for me. Or it can tell a PLC to actuate a pump to add water or to add polymer. All automated, don't have to pay attention to it.
Got it. Got it. Yeah. And that works not just on induction equipment, just to be clear, right? I mean, you can do this on a quench tank, whatever.
Anywhere
Okay.
I can put it on a polymer quenchant, for instance.
Gotcha.
Control
Gotcha.
polymer. But
Okay.
most commonly, it is being used on, it's being used on induction. In fact,
Gotcha.
It's standard on some of the induction hardening equipment that's being.
So basically just a simple human machine interface or human quench fluid interface. It's going to tell you whether it's within spec or not. If it's not in spec, the green light goes out, the red light comes on, and potentially you
sounds an alarm or sounds some sort
right.
of annunciation, whether it's visual or audible or both.
Yeah, and you either fix it manually. You either fix it manually, or you've got it programmed so that a PLC can make whatever adjustments.
Contact closure that you can tell a PLC to do some.
Yeah. All right, good. All right, let's hit one other main topic before we wrap up today. And you've already kind of hinted at it, but I think it's something that's important. We've talked a lot about brain drain in the industry and the fact that and you and I actually spoke offline here not too long ago about metallurgy programs versus material science programs, and the fact that sometimes material science graduates don't necessarily have a full grasp on what metallurgy is and how it works. When companies that are manufacturers in their own in-house heat treat, they're needing help. What about, how are they going to get training? Where can, in fact, they go to get questions answered, things of that sort? And how bad is that problem?
Well, one, it's a global issue. All right.
Okay.
Metallurgy is kind of like a forgotten science.
Yeah.
The reason now, and I was one of the last from at Ohio State to actually graduate with a metallurgy degree. Metallurgical engineering. Right after that, they changed to material science. The reason why is because one of our illustrious funding or grant funding says, we already know everything there is to need to know about heat treatment and metallurgy. All right, we need to be focusing our energies on nano this or green this or additive manufacturing or whatever kind of buzzword. In other words, you toss in something, toss in those buzzwords and you can get a grant. So in other words, it's because of the universities chasing the government cheese, okay, when really what the industry needs is people who have a strong grasp of the metallurgy of something. For instance, we have when I went to school back in the dark ages, and this is about 1980, call it, back when we still use slide rules. I still have mine. We were actually had whole courses, multiple semesters on heat treating. How does a steel react when I change the quench rate? We have, the different microstructures you get. Looking at the microstructure, what do we get? Now, with a material science degree, what we were exposed to in multiple semesters, they may get mentioned in a single lecture.
Yeah, yeah. And spend the rest of the time talking about plastics, polymers, composites, and the highfalutin new stuff, which is important, but
I mean, to
it's
give you
certainly,
an idea, all right,
yeah,
I had a customer. They were having roughly 95% cracking. And so they asked me to help. And they're using our quenching, all right? And what they were doing is that they were taking the parts and they were putting them into the high temperature, the austenizing furnace. Okay. They would then quench them into our polymer quenching. And these were parts like 4340, big parts, you know, big parts. They only had the one furnace. So then what they would do is after they quench it, they take up the parts, then they would put them outside in the snow. And so they could let the furnace cool down so they could then temper them. You know, and usually take overnight. So that when they come around in the next morning, all these big, expensive, large, and we're talking, you know, several 100-pound parts, were sitting there in multiple pieces because of quench cracking. So they wanted to understand why this was happening. So I go in there and I meet with their metallurgist. And I said, okay, what the problem is, you're having an issue with with quench cracking, which is due to, you know, quench cracking is due to the transformation of martensite, and you need to get rid of the residual stresses by putting it in temper immediately. The metallurgist looked at me and asked me, what's martensite?
yeah,
At which
not
point
a good sign.
I had to control my,
Yeah, your inner Scott.
in my, yeah.
Yeah,
And I asked her, where did she go to school?
yeah.
And she went to another school, which, can I mention the school?
Yeah, go ahead.
Okay, she went to Carnegie
What?
Mellon. Okay, she
Sure.
went to Carnegie Mellon.
Not that it's not a good school. It's just
Oh, it's
your
wonderful
point being,
school. No,
your
it's
point
wonderful.
being they're not covering the metallurgy that they need,
That's
right?
right. Right.
Yeah.
Now, I looked at her and I said, you know, I know a lot of the professors there. In fact, I flunked out at Carnegie Mellon. Like, you know, I mentioned it. I had lousy grades. I flunked out at Carnegie Mellon. Okay, I was accepted, flunked out. So I know. I mean, in fact, you know, MetTrans is by, you know, Dave Laughlin, who is at Carnegie Mellon, who is a wonderful person. I think he may have retired now. Wonderful professor, and he gave me my first metallurgy program. He's also been very supportive to me throughout my career. But I looked at him and I said, you know, as I recall, they had, you know, we were taught these courses. I mean, I had Masowski, I had, you know, Laughlin, I had a whole bunch of people that were, you know, well up in the. And she said, looked at me and says, oh, well, it was a material science degree and I took the ceramic option. So anyway, we had to go through and do all the training, you know, what's required and all the stuff. And we got it. So understood what was going on, understood, you know, the ramifications of different quench rates on, and got that all resolved. And then I talked to this when I was working on my, you know, afterwards, I talked to one of my professors who has since passed away at University of Missouri-Rolla, or now known as Missouri Science and Technology or something like that. Right? Missouri Institute of Science and Technology. So MITS or something like that, maybe. Yeah, I guess. I'll still call it University of Missouri-Rolla. And he said, that's unfortunately the truth. if you want somebody that's knowledgeable in heat treatment, don't hire a material science person. Hire a mechanical engineer, because at least they will be exposed to it.
Yeah, yeah. And I think you mentioned that's a good point. That's a good point. It's possible that the mechanical engineers are going to have more exposure to at least the effects of heat treat and understand heat treat more than maybe materials engineers who may not even, may have got one course. You'd mentioned before, Scott, that there are only a couple of schools in the US now that still maintain an actual metallurgy degree. Yep. Do you recall who they are?
Yeah, I believe the University of Missouri, Rolla.
Okay.
They still are Missouri Institute of Science and Technology.
Gotcha.
In beautiful and scenic Rolla, Missouri.
Okay.
There is University of Arizona.
Okay.
But I believe they are focused strictly on mostly mining.
Yeah, because there's a heavy metallurgy emphasis in mining as well. So yeah. Mm-hmm.
There is University of South Dakota.
South Dakota, I think, yeah. Mm-hmm.
And maybe University of Idaho.
Okay.
I'm not sure on that one, but
Colorado School of Mines. Colorado School of Mines.
Colorado School of Mines, sure.
I think that they at least used to. I don't know that they still do.
They still do.
Yeah.
That's for colleges.
So I guess an application here is for companies who are looking to hire people to help them with metallurgy, because what we're talking about here is training and getting the brain drain. Is be very careful who you're hiring and where they came from and how, if they're, not to say that all materials engineers are not worth their salt, because that is not the case. There's going to be plenty of them, but you need to ask the question, how much exposure, what has been your experience in metallurgy specifically? All right. I think that's the point.
And I'll tell you what, all right, now the industry right now, okay, it's a bunch of old guys, all right? We're retiring. I'm going to be retiring probably in the next up to 3 years. All right. But if you look at other people in the world, we're all getting up there.
Yeah.
And the young people to replace us, all right, we'll have to be knowledgeable. Otherwise, we're going to repeat all the same mistakes all over again.
Right. Well, I want you to know
tragedies associated with it.
I want you to know there are a lot of young people coming up in the industry right there, 40 under 40. So there are some good people. It's amazing. But your point is very well taken. There's a lot of
one of those 40 of 40 has been hired or has been brought along.
That's right. Sergio.
Yep, Sergio.
Sergio, wonderful. Okay? Yeah, that's good.
Now, that said, somebody that is very knowledgeable in heat treatment.
Yeah.
Because it's still going to be needed, whether you're doing, for production of gears, not necessarily for transmissions, but gears for wind turbines or
exactly.
Whatever. Mm-hmm. Heat treatment of turbine blades, heat treatment of whatever. Somebody who's knowledgeable in heat treatment, a young person, will be able to write their own ticket.
Yeah. I agree with you. Yeah.
One of the beauties of heat treatment that I've had, I've never had to worry about losing my job. I've never had to worry about being laid off.
Yeah.
And I've been through some ugly layoffs. We went to McDonnell Douglas and we had 64,000 people at one time. The next morning we had 30,000 left.
Wow.
In one day, they lay off 35,000 in one location.
Wow.
So, I've never had to worry about being laid off.
Yeah.
I've never had to worry about, all right, if something happens, will I be able to find a job?
Yeah.
Never had that issue.
Not been an issue for you. That's great.
And I think that will be true of any young person in heat treating.
Yeah.
You'll always be able to find a position.
Yeah, that's good. Well, that's great, Scott. I appreciate it. So just to wrap this one little segment up as far as training goes, the fact of the matter is, if you don't have in-house resources to help you understand heat treating and or the quenching aspect of it, I think point being, there are consultants out there that can do it. There are quench companies like Quaker Houghton, for example, who are
And
more
heat treating societies, for instance, ASM Heat Treating Society.
ASM. Yeah.
And since this is a global,
Yeah.
all the heat treating societies, whether it is the Chinese
Sure.
Heat Treating Association, the Chinese Heat Treating Society, there are two of them, and they're huge.
Right.
All right.
Right.
ASMET, which is the Austrian, IWT, which is the German, the Italian Heat Treat Society, the Czechoslovakian,
Right.
the Indian Heat Treat Society, which is actually part of ASM. All those societies have their own training programs.
Right.
And
Right.
they're good. I've taught some of them. And other people have taught, but take advantage of your local heat treating society.
Yeah. Right. And if you
they
need
can
help,
you do the training of your own people, or
right.
you can use the consultants.
That's right. Yep. And I was going to say to anybody listening, if they need help finding those resources, you feel free to call us. I'm sure that Bethany will put some information in this podcast about how you can get a hold of us and help. And we can, if nothing else, we can put people in touch with you, Scott, which leads me to the final question. How much information are you willing to give away as far as people contacting you? And don't worry, even if you're probably not really allowed to retire. So even if you do, these people will find you. So how can they contact you?
Well, I mean, you have my email address. I mean,
yes, we'll put that up on the screen.
MacKenzie at Quaker Houghton. All right.
Right.
Right now, I'm not taking any consulting positions. I get asked routinely.
Yep.
And part of that is because it's a conflict of interest with my existing job. All right.
Sure.
I can, if you're using our quenchings, I can help you.
Right.
Or if you're looking to use our quenchings, I can help you.
Right.
And that isn't just choosing a quenching. All right. I mean, obviously, I can help you select a quenching if you're unhappy with your existing product.
Right.
But I can also help you, minimize distortion, better reproducibility, better properties. Whether that's, now we do, company can come to us and ask for, CFD modeling of the quench tank.
Sure.
Right? We can do that. Or we can do that as part of it, doing the modeling of the part. We can do that. Right? And we can do it, tie them together as best we can, depending on the conditions of the quench tank. And we can do that on a ASB basis. So I can help you in that fashion, but there are also other people out there, Andy Bank at Airflow Sciences, which can do CFD work, Dante Technologies, Transvalor in Europe, and here in the US can also do stuff. I mean, we happen to work with Transvalor. They can all do that. They can do it for a consulting fee. So it can be done. I mean, when I get out of, I decide to figure out what I'm going to do after. When I figure out when I'm going to retire, and then I try to figure out what I'm going to do after I retire. Then I'm
Yeah. Well, we'll find you. Don't worry. You won't be able to hide. So
that's
very good. What's that?
That's what I'm afraid of.
Yeah, exactly. Very good, Scott. Well, I appreciate it. Any closing comments you'd like to make? Anything we missed that you'd want to include in here? I think we've hit on most of the major stuff we were thinking about.
I mean, probably the biggest thing is encourage your young people to go to conferences. And I'm not just talking about stuff where they're laying out a whole bunch of equipment. Right? I mean, just an exhibition so you can kick and look at equipment. They need to go to the events so, one, they can meet other experts, so they can be educated, and I'm not just talking about taking an ASM course, but I'm talking about going to the conference, being able to ask questions of other experts, as well as talk to their peers. What are the problems the peers are having? More than likely, it's the same sort of problem. And be able to expand the horizon by seeing the conference proceeding, etc. Encourage them to go to those sort of things, and also submit papers, etc. Because that's the only way they'll grow. And that's what you want, is that you want the people to grow within the organization and encourage them to grow within the organization. So
Right.
they become more of a value to that organization.
Yeah. There's no better way to learn than to teach. Once you decide you got to teach, you got to learn the stuff. So that's great. Well, you've done a great job of that over the years, Scott. I know there's many people in the industry who've appreciated your expertise, and we certainly appreciate you being with us here today. So thank you very much for your time, and we'll look forward to talking with you again. Don't retire too soon. We'll need you here. So stick around.
Okay. Thank you.
We hope you enjoy listening to today's episode with Scott. Heat Treat Radio is on Spotify, Apple Podcasts, SoundCloud, iHeartRadio, Podbean, and the website www.heattreattoday.com/radio. To learn more, head over to www.quakerhoughton.com or email Scott at scott.mackenzie@quakerhoughton.com. You can also email me and I can put you in touch. My email is bethany@heattreattoday.com. You can also reach out to me if you have a new or interesting idea for our next Heat Treat Radio episode, or if you'd like to sponsor. Again, my email is bethany@heattreattoday.com. August is for automotive, and after listening to this episode, you can go check out the digital edition of Heat Treat Today's automotive print magazine that released this month. Find the resource at www.heattreattoday.com/digital editions. Heat Treat Radio would like to thank Heat Treat Bootcamp for sponsoring this episode. Find out how to enroll in this basic training at www.heattreattoday.com/bootcamp. This and every other episode of Heat Treat Radio is the sole property of Heat Treat Today and may not be reproduced in part or in whole without advance written permission from Heat Treat Today. And I am Bethany Leone. Thank you for listening.